In the last section of this chapter, we talked about exponential growth and worked with those models. But as you know, exponential growth in a natural environment is just not practical. There's some point at which that population just can't grow anymore. So we need another model, and we use logistic growth a lot of times for population models. It grows exponentially at first, but then it reaches a limiting value and it kind of levels off. And that's much more practical. Before we can talk about logistic growth in calculus, we need to be able to work with partial fraction decompositions. This is a method for, it's big words, but it's just a method for finding the antiderivative. Usually we're going to end up with a fraction. We're going to have a differential equation that is a polynomial in the top and a polynomial in the denominator. And none of our techniques so far are going to be adequate to cover all of these kinds of quotients. Now, some of our quotients we could use a substitution, a trig substitution or something. So you don't want to throw those methods out. They might work for some of the quotients. But if you get to a logistic growth model, then it's definitely going to be something that you need partial fractions to be able to find the antiderivative. They do tell us in this box here that the degree of the numerator needs to be less than the degree of the denominator. If it's not, then there's some things that we can do. We're going to look at an example like that, so it's really not limited by that. First thing we're going to do is look at an example and just go through the algebra of the partial fraction decomposition. Once we do that, the calculus will be easy because the partial fraction decomposition will change the way our function looks, change the way the integrand looks, so that it turns it into something that we can use our other methods for finding the antiderivative. But as this function stands right here, a u substitution would not work, and that's basically all we have. It wouldn't be integration by parts because we don't have things multiplied together. So we're going through the algebra of this, and then in the next example we'll look at the calculus as well. So partial fraction decomposition is just taking a fraction that's a single fraction and rewriting it as a sum of fractions that have linear denominators. So basically we're undoing finding a common denominator and writing it as a single fraction. So first thing we need to do is factor this denominator into linear factors. So we're going to have 2x times x for the x squared. I need a 3 here. The signs are alike and they're both going to be negative. So I'm going to put a negative on the 3, so I have negative 6x, and a negative on the 1, so I have negative 1x, and that gives me negative 7x in the middle. So I'm rewriting f of x with some numerator that I don't know yet, and I'm going to use this factor, this linear factor, for one of the denominators. Doesn't matter which one goes under a and which one goes under b. And then we're going to add to that another fraction that has some unknown numerator, and we're going to put the other linear factor for that denominator. Now, if I had started with this and I wanted to get a common denominator right here, then I would multiply this fraction by x minus 3 on the top and on the bottom. And I would take this fraction and I would multiply it on top and bottom by the 2x minus 1, by this denominator right here. I'm only interested in the numerators because I already know what's going on in the denominators. So I'm going to pull the numerator parts off of that. I'm going to take the a times the x minus 3. And then I'm going to say plus the b times the 2x minus 1. And then that has to equal this numerator that you have on the single fraction. The next step is to let x be 3 so that this is 0 here, and that takes that term out, and I can solve for b. I also need to let x be 1/2, so that if x is 1/2, this is 0, takes this term out, and I can solve for a. So you're always going to let x be the roots of each of the linear factors. Okay, and that lets you know what a and b are. If x is 3, then that's going to 0 out, and I get b times 6 minus 1, just substituting a 3 for the x. So 6 minus 1 is 5. I have 5b is equal to, don't forget to let x be 3 over here as well. So 3 minus 13 is negative 10. That means that b is equal to negative 2. Do the same thing for the x equals 1/2. If x is 1/2, then that zeroes out right there. And 1/2 minus 3 is negative 5/2 times a. and that's equal to 1/2 minus 13 is 26 halves, so that's going to be negative 25 halves. I'll multiply both sides by 2, and then divide both sides by negative 5, and a is equal to 5. So now I can go back up here, and I know that a is 5, so I have 5 over 2x minus 1, plus b is negative 2, so I can write that plus, or I can change that to a minus in between and put 2 over x minus 3. And 5 over 2x minus 1 minus 2 over x minus 3 is exactly the same as this single fraction up here. And now if I wanted to integrate, I could integrate term by term, and then I could just use a little u substitution on this one and on that one, and I could find the antiderivative. We're not going to do that in this example, but that's what partial fraction decomposition does for you.